Okay, so persisting with this encrypted computation, one of the poster person applications of this primitive is the field of personalized medicine, where maybe you want to use links between DNA and disease in order to do medical research. So right now there is a lot of DNA data available, but people are obviously worried about sharing this data because it's obviously very sensitive data. So the question is what to do. So public key encryption does not work, okay, because it will not let you compute on encrypted data, and there are many problems with public key encryption in this situation. So for instance, if I have many different users, right, then how do I encrypt this data? So if it is like, let's say it's all of you with your vectors, okay, what mechanism is used for encrypting it? I mean, if you all encrypt it to my public key, then I can open and read all of it. If you all encrypt it with your own public keys, then it will not talk to each other, right? There is that problem. Another problem is all or nothing access. So let us say we encrypted it somehow using some public key. For a second, let's not think about whose public key, but there's corresponding to that only one secret key, and if I have that secret key I get everything. If I don't have that secret key I get nothing. So this question is actually beyond the question of computing. Okay, try to get this. So it's different from the question of whether I can compute on the ciphertext or not. Even if I can compute on the ciphertext, this all or nothing decryption could be a problem, right? So for instance, in this application of personalized medicine, maybe I can, okay, let's just go back to this. So in the application of personalized medicine, what I might want is that I might want to compute I want to do some study on the data, like I want to see what is the correlation of this ethnic group, this age bracket and this disease, let us say, right, and how does it relate, is there a pattern in the DNA that lets me predict it, for instance. So now I don't want, so let us say that I can even do this computation while the data is encrypted, let us say that. Even then, if there is a single key that decrypts everything, then this is a privacy concern, right, because not only am I learning the output of the computation, I could potentially use the same key to learn the input as well. So then I have to rely on the fact that the input is never made available to the person with the key, which is generally problematic. So in such a scenario, what we are really wanting is a more powerful notion of encryption, where let us say the secret key corresponds to some sort of functionality, like this medical study that I was talking about. So any algorithm is finally a circuit, right? So, or a Turing machine, let us think of circuits. So the point is that whatever algorithm it is that you want to run on this data, I will give you a secret key for that algorithm, right, and the ciphertext now can correspond to whatever genomic data or whatever, but it will now be the case that even when I get this encrypted data, not only can I compute on it, but I will be forced to only compute the function that I have the key for. So I can only learn the output that I have the key for. So what this means is that if my key corresponds to some function f and the ciphertext corresponds to some input x, then decryption recovers f of x and nothing else. Okay, so here is an example that f is maybe the age distribution of people with lung cancer and x is a particular user's disease profile. Okay, I have another example of this. This is called functional encryption. I have another slide for it. So many of us are looking confused. So let's look at this. Okay, so encryption takes some, think of your genomic sequence. Okay, we are encrypting that. And now key generation corresponds to some function. okay, and decryption gives us f of x, right, and security says that I should not be able to learn anything about x from the ciphertext. So, a little more formally, encryption of x0 and encryption of x1 should be indistinguishable. So, now how does this go to personalized medicine? So, let us say that we have genomic data of the instructor and the TAs, okay, and the key generation algorithm gives me a secret key for some medical research algorithm. Okay, so now when I decrypt, we take all these ciphertexts and we just get f of x. Now, what is f of x? It's just the results of the study in the clear. Is it clear? For instance, if we encrypt everybody's grades here, right, and I publish these ciphertexts on the course web page, what is everybody's score in homework 1, homework 2, whatever be the case, right. Now, I do not want to give a key that leaks everybody's scores to everybody, right. So, what can I do? Well, I can give a secret key that lets you compute things like what is the average, what is the standard deviation, stuff like that, which is okay for everybody to compute, but people's individual grades are hidden. So, in this example, people's individual genomic profiles are hidden, but the key allows me to compute some lossy information, some statistical information which is not leaking anything about individual users. So, you see how this is in its limit it is extremely powerful, right. You could do, for instance, now you have all this Aadhaar data of all or so many citizens of the country. You could imagine if this were to work perfectly somehow. I mean, at the moment constructions are very inefficient, very far from being practical, but if this were to somehow be very, very practical, then you could imagine doing social science studies. Like, let us say the government started some scheme to raise the, I do not know, the income of some community of people or something like that. Now, you can perform these studies on encrypted data. So, people's age, income, religion, various things which might be sensitive need not be revealed. You can only see, you can figure out the algorithm that you want to run and provide a key simply for that algorithm alone. Yeah.
Wouldn't this require that the key generator is not compromised?
Very, very good question. So, the question is, doesn't this somehow assume that the key generator is not compromised, because the one who is generating the keys might be able to decrypt everything. So, that is a very good point. The answer to that is that you have reduced the sort of the vulnerability point to this key generation thing, and the key generation can be done using multi-party computation. But the cool thing is that this key generation, right, it is something that only needs to be done once per key, for example. So, if all of us participate, so all of cryptography is about distributing the trust, right. You do not want any one party to be able to, it is more like a democracy than a dictatorship, right. You want to spread the power and hope that there is sufficient honesty in the system that the honest thing gets done. So, in this example, the key, it is true. So, what can the encryptor do? The encryptor can only encrypt. This is using a public key. So, there is no security threat there. The key generator clearly has some privileged information that is allowing it to generate keys for various different functions, right. Can this privileged information be used to break the ciphertext? Yes. So, what will we do? The key generation algorithm, we will not give it to one person. We can distribute it amongst some group of people and give a kind of guarantee. This is actually what we were doing in the secure elections example, that we can give a guarantee that as long as, let us say, you know, I don't know, n over, for example, as long as n over 2 people are honest, this you know, the master secret will be secure. So nobody knows the whole secret, everybody knows some piece of it. So the question is it like the Tor anonymizing network where, you know, you go from one to the other and everyone is adding their own encryption? It's much simpler than that. So, you know, something very simple, like let me say that, you know, I have some secret, okay. So let's call this is my secret S. If I just, you know, write S as S1 plus S2 plus S3 plus S4, okay, where these are all random subject to their summation being equal to S, right. This is what is called a secret sharing the secret amongst many. So now what can I guarantee? I can guarantee that you know, if any one or two of these are leaked, even 3, as long as all 4 are not leaked, right, I don't actually learn anything about S. So this is a vague answer to the question, because we cannot give a precise answer unless we look at a candidate scheme. The precise answer is that you can do key generation uses multi-party computation. And multi-party computation basically means that the secret is split. So as long as you know, a sufficient number of people are honest, whatever sufficient means depending on the protocol, you will get secrecy. That's a very good question. Yes.
Just a little clarification. So right now we are talking about the all or nothing access, right?
We are not, right, because we are computing f of x. So this is not all or nothing.
Computation happening without decrypting the data, right?
That is where the magic lies. So the question is that first of all, the first question was, right now we are talking of all or nothing decryption. The answer is no, we are not. In fact, we are not, emphatically not talking of that, because I am giving you a key that gives you f of x but not g of x, and in particular definitely not x itself, right. So we are not talking of all or nothing, that is thing 1. Yeah, the second question is, how is the computation happening?
So effectively here you are limiting the access to the information available to all the other parties. You are just giving out f of x because your key only decrypts and gives you f of x.
Yeah, but that is a feature, not a bug, right. F could be the identity.
Yeah. So my question is, how is the computation, where is the computation happening? Like,
The question that he is asking is, where is the computation happening? The computation is happening during decryption. So during decryption, I will compute f on the ciphertext. I will get a ciphertext for f of x, and then I will use the key for f to recover f of x. And the guarantee is that this key will only work if you honestly computed f, and otherwise it will not work. Does that answer the question? You still look confused. So what's the question? You may not.
f on x without actually accessing x.
That's the whole point.
That's what I think. That's what it's called.
The whole point is that you are computing f on x without accessing f of x. So this is why I keep saying this is surprising. It should be surprising. What you are doing is, you know how to compute, you have x. Let us say if you have x, what you know, I know to compute f of x, okay. After that I can compute enc of f of x, correct. what I am telling you is that I can swap these steps. I can compute enc of x first and put f on top of that. So, it is a big breakthrough. It was a big breakthrough in cryptography when it first happened. I mean, there are various flavors in which this, you know, animal or whatever flavors, but there are various versions of this, okay, which we at this level of abstraction we cannot discuss. But the point is that I can compute on the data while it is encrypted, okay. I could do this with all or nothing access. Actually, that is a much simpler problem, though it was a big breakthrough in its own right. So, with all or nothing access, this is called fully homomorphic encryption, and this year's Gödel prize was to the people that you know, figured this out. And fully homomorphic encryption tells you that you can compute on encryption of x and get encryption of f of x, and you have all or nothing access if you have the key. So, if I have the key, I can decrypt the f and get f of x, but I can also decrypt and get the original x. What I am talking about right now is even more powerful than that and objectively much harder to construct. Okay, so this is the primitive of functional encryption, where you encrypt on the data. So, you still get I mean, you compute on the encrypted data, you still get a ciphertext with f of x inside it, but you do not get a single key which works for everything. You get restricted keys, you can delegate, you can give keys for specific things, right, and that makes it, in fact, even the security is very hard to define. So, what he is saying is that this is this sounds very powerful, or I do not know what, you did not give a particular word, but
It does sound much harder to do, because now
I mean, it is in fact infinitely harder to do, but the reason for that is that previously you had a ciphertext for x and the guarantee was that you could not get x out of it without the secret key. Now, I am giving you the ciphertext for x, I am also giving you a way to compute f of x, but I still learn nothing about x beyond f of x. So, this is obviously a generalization first of all, and it seems like a very powerful generalization. It in fact is a very powerful generalization, and this is a very active area of research right now called functional encryption. Okay, so the question is that isn't it double encryption, because you are taking x and converting it to f of x and then you are again encrypting on top of that. So, no, your understanding is incorrect. So, here are you looking at this picture here? So, in this picture there is no enc of x at all, right. So, what I was saying was that if I myself pick x, I myself pick f, I can compute f of x. After that I can certainly encrypt f of x, and this was going to be in comparison to I encrypt x, I compute f of enc of x. This is not 100% precise, but we will go with it. This gives me enc of f of x. You could think of it incorrectly, but almost correctly, as saying that f and enc commute. This is not correct, but it is the right idea. So, there is no double encryption at all, there is only one encryption. Either you encrypt after computing f on x, or you encrypt before. You can get to enc of f of x, you can get to it via these two paths. One is that you do enc of x and compute f, one is that you do f of x and then compute enc. Does that answer the question?
Yeah, yes.
So, I mean, if it seems very if it seems sort of surprising, it is. So, cryptography is a really powerful field, right, and this is why also I wanted to show you this, because most people do not realize what are all the things that are possible, all of them or many of them being very unexpected. All right, spam detection on encrypted emails. So, I think we have discussed this example quite a lot already. So, we will move on. Okay. So, yeah, basically you have encrypted email, but you can have a key that checks if the encrypted email is spam or not. So, you could give this to your to the email gateway. So, they can't read your messages, but they know to discard the email if it is spam. Yeah, and this is fully homomorphic encryption, which I already told you about. So, this is all or nothing access. So, this is when I can switch F and enc. So, I can compute F after encrypting X, but I have only a single key and this key works for everything. Okay, whereas previously what I was showing you was the even more advanced version, which even lets you get partial decryption keys. Okay, so you can see that functional encryption will capture this, right, because it just means that my key generator only needs to support the single identity function. So, whatever ciphertext I get, it should be able to decrypt that. Yeah, so yeah, this has an expressive functionality, compact ciphertext, and for all or nothing decryption, this is perfect.